The modern battlefield has been fundamentally altered by an asymmetric nightmare. Picture this: a highly sophisticated billion-dollar electronic warfare net designed to sever the navigation links of advanced cruise missiles. Now picture that net being completely bypassed by a crude, moped-powered delta-wing drone costing less than $50,000. This is the terrifying reality of the Iranian-designed Shahed 136 and its Russian derivative, the Garand 2. These mass-produced expendable loitering munitions have become the defining symbol of the industrialization of attrition. They are slow, noisy, and built from consumer-grade electronics, yet they consistently penetrate the world's most contested airspace. How does a cheap piston-engine drone powered by a commercial 50-horsepower motor reversed engineered from a German design fly straight through a wall of military-grade jamming? The answer lies in a masterclass of asymmetric navigation engineering. It is a brilliant, layered synthesis of adaptive digital antenna arrays, brutal dead reckoning, and autonomous aerodynamic compensation. Welcome back to the SWaP-C report. Today we are tearing apart the navigation architecture of the Shahed 136 to understand the raw math and hardware that makes these cheap drones deadly, even when they are flying completely blind. The primary guidance of the Shahed 136 relies on a civilian-grade Global Navigation Satellite System, or GNSS. Because these satellite signals travel from space, they possess an extremely low-power spectral density by the time they reach the Earth's surface, making them incredibly fragile and susceptible to terrestrial jamming. To survive, the Shahed utilizes a specialized piece of hardware known as a Controlled Reception Pattern Antenna, or CRPA. Specifically, the Russian Kometa-M module. A CRPA does not just passively receive signals. It actively manipulates the radio frequency environment using spatial filtering. The system features an array of independent antenna elements, often 8 or even 16 in newer iterations, each processing incoming RF signals. These signals are first down-converted to an intermediate frequency and digitized by high-speed 16-bit analog-to-digital converters. These massive digital streams are fed into a field-programmable gate array, often a commercial Xilinx or Altera device, which executes complex null-steering algorithms at lightning speed. The objective of the null-steering algorithm is to calculate a complex weight vector that suppresses interference while maximizing or maintaining gain toward the satellites. The received signal vector at any given time is modeled as the steering matrix multiplied by the vector of signal amplitudes plus the receiver noise. To defeat a jammer, the system continuously computes the spatial autocorrelation matrix of the incoming signals, averaging the samples over time. Using the power inversion algorithm, it seeks to minimize the output power. Using Lagrange multipliers, the optimal weight vector is found. When this weight vector is applied across the array, it creates a null, a sharp dramatic drop in antenna gain of up to 50 decibels precisely in the angular direction of the hostile jammer. This mathematical blind spot effectively mutes the overwhelming electronic noise, allowing the faint, true satellite signals arriving from the upper hemisphere to bleed through. But what happens when the electronic environment becomes so saturated that even an advanced 16-element CRPA cannot isolate a clean signal? When the drone enters a total dark zone, its primary navigation is severed, and it must rely entirely on its secondary pillar, pure dead reckoning via the inertial navigation system, or INS. The Shahed 136 relies on cheap commercial off-the-shelf MEMS inertial sensors. This is the brutal reality of blind flight. The flight controller's navigation computer must mathematically integrate the raw IMU data to estimate the drone's position, velocity, and attitude. First, it performs attitude integration. The raw angular rates from the gyroscopes are used to update the attitude quaternion. Next, the raw linear acceleration measured in the body frame must be rotated into the navigation frame while carefully subtracting the local gravity vector. Finally, this corrected acceleration is integrated once to find velocity and integrated a second time to find the physical position in three-dimensional space. Commercial MEMS sensors possess inherent physical limitations, inducing severe stochastic errors like bias instability and angle random walk. In this continuous integration chain, even a microscopic constant bias in the gyroscope results in an orientation error that grows linearly with time. Because the drone's orientation is slightly misjudged, Earth's massive gravity vector is incorrectly subtracted from measured acceleration, causing horizontal acceleration errors. This horizontal acceleration error is then integrated twice by the flight computer. Consequently, the final position error grows with the cube of time. For a cheap Shahed drone with a consumer-grade gyro bias, the position error after just 10 minutes of blind flight can easily exceed several kilometers. This accumulation of error is quantified by Circular Error Probable, or CEP, the radius where 50% of impacts statistically fall. Assuming horizontal position errors are independent Gaussian random variables, the radial error follows a Rayleigh distribution. If the standard deviation of the position error reaches 15 kilometers after 1 hour of GPS denial, the calculated CEP expands to a massive 17.6 kilometers. Without periodic satellite updates, the Shahed 136 is completely incapable of precision strikes against specific buildings over long distances. It becomes an area weapon, limited to saturating massive urban centers or sprawling energy grids. In pure dead reckoning, sensor drift is not the only enemy. The atmospheric boundary layer presents a terrifying aerodynamic challenge for a slow-moving munition. With a relatively slow cruise speed of about 150 to 185 kilometers per hour, a modest 30 kilometer per hour crosswind can physically push the Shahed 136 miles off its intended course within minutes. Because the drone is effectively blind, it cannot see the ground to know it is drifting laterally. To maintain its glide slope and heading toward the target, the autopilot must continuously solve the wind triangle. Navigation geometry relies on the vector addition of true airspeed and wind velocity equating to ground velocity. While GNSS is available, the autopilot runs an extended Kalman filter, actively learning the wind vector by comparing its ground track against commanded airspeed. Once the drone enters the dark zone, it freezes this last known wind estimate. Using proportional integral derivative, or PID control loops, the autopilot calculates a wind correction angle, frequently called a crab angle. The required heading to maintain the desired track is computed using inverse trigonometric functions based on the ratio of wind speed to airspeed. The flight control system violently actuates the hinged rear fins and vertical stabilizing rudders via high-voltage servos, permanently adjusting the drone's heading into the wind. Through constant aerodynamic compensation, the drone's net velocity vector stays aligned with the mathematical glide slope, fighting the air mass to maintain its trajectory completely blind to the outside world. The navigation and anti-jamming engineering of the Shahed 136 represents a masterclass in asymmetric warfare. It is not built on a single, exquisite superweapon technology, but rather a resilient, layered architecture. By fusing adaptive CRPA null-steering to protect fragile satellite signals with COTS inertial sensors for blind dead reckoning and pitot static systems for atmospheric compensation, these systems achieve an industrialized, good-enough perfection. The poor man's cruise missile ensures that even in highly contested environments, it will find its mark. If you want to dive deeper into the engineering of modern conflict, hit that subscribe button. This is the SWAP-C Report. We will see you next time.